Now let us discuss the quantum mechanical model of the atom from a conceptual standpoint. The Bohr model does not work well for atoms that have more than one electron. Since it cannot accurately predict the emission spectra of multi-electron atoms, scientists knew that the Bohr model was still incomplete and needed improvement. The quantum mechanical model builds upon the Bohr model by applying wave-particle duality to electrons. Just as light is a wave that can behave like a particle, electrons are particles that can also exhibit wave-like behavior. Erwin Schrödinger used mathematics involving probability to develop what are called wave functions, which describe regions around the nucleus where there is a high probability of finding an electron. As a fun side note, there is a website called academictree.org that tracks academic lineage, who earned their PhD from whom. Using this website, I discovered that I am separated by 6 academic degrees from both Niels Bohr and Erwin Schrödinger, and by 7 degrees from J.J. Thomson and Ernest Rutherford, who developed earlier atomic models. As we move into the quantum mechanical model of the atom, there are 2 vocabulary words that sound very similar but mean different things: orbits and orbitals. The Bohr model uses orbits, which are defined paths around the nucleus, similar to how planets orbit the sun. In the quantum mechanical model, electrons do not travel along fixed paths. Instead, they exist in orbitals, which are regions of space where there is a high probability of finding an electron. Orbitals reflect the wave-like nature of electrons. Just as waves had peaks and troughs, orbitals have regions of high and low probability. The key difference is that orbitals are three-dimensional rather than two-dimensional waves we typically draw. This probabilistic view of electrons is a central idea of the quantum mechanical model of the atom. In the quantum mechanical model, we still have shells just like in the Bohr model. These shells are numbered starting as n is equal to 1 closest to the nucleus, with higher numbers further away. These shell numbers can now be called the principal quantum number. Unlike in the Bohr model, each shell now is divided into subshells. For the n is equal to 1 shell, there is one subshell labeled S. For the n is equal to 2 shell, there are 2 subshells, S and P. For n is equal to 3, there are 3 subshells, S, P, and D. For n is equal to 4, there are 4 subshells, S, P, D, and F. The number of subshells is always equal to the shell number. Because the quantum mechanical model is difficult to draw due to the complex orbital shapes, we can enhance the Bohr model visually. If we zoom in on the n is equal to 1 shell, we have 1 subshell. Zooming in on n is equal to 2, we see S and P subshells. Zooming in on n is equal to 3, we see S, P, and D. And for n is equal to 4, we see S, P, D, and F. This pattern would continue for higher shells. Within each subshell are orbitals. I will represent orbitals using lines. An S subshell always has 1 orbital, and a P subshell has 3 orbitals. A D subshell has 5 orbitals, and an F subshell has 7 orbitals. Notice that the number of orbitals is always an odd number. You may be wondering why the letters S, P, D, and F were chosen. These letters come from historical descriptions of atomic emission spectra: sharp, principal, diffuse, and fundamental, although you don't really need to know that. Orbitals within each subshell take on unique shapes. Orbitals outline areas of high probability of finding an electron. Orbitals in S subshells are always spherical. Orbitals in P subshells are shaped like dumbbells. And most D orbitals have 4 lobes, like clovers, while f orbitals take on even more complex shapes with additional lobes. When comparing an s orbital in the first shell to an s orbital in higher shells, the shape stays the same, but the size changes. An s orbital in the fourth shell is much larger and much further away from the nucleus than an s orbital in the first shell. Electrons in higher energy orbitals are more likely to be found further from the nucleus. The same pattern is true for p orbitals, d orbitals, and f orbitals. Orbitals in higher energy shells are the same shape, just larger in size, and electrons are more likely to be further from the nucleus. This diagram summarizes the relationship between these terms. The shell number is also called the principal quantum number, symbolized by n. Subshells are labeled S, P, D, and F, and each subshell contains a specific number of orbitals. S has 1, P has 3, D has 5, and F has 7. The Rydberg equation does not work well for atoms with more than one electron because the energy levels of S, P, and D are no longer equal. Electron-electron interactions cause the energy levels to shift. As a result, every element has a unique set of energy levels, which is why each element has a unique emission spectrum. Fortunately, the periodic table is organized in such a way that we do not need to memorize the energy order for any element. We can use the periodic table to determine the general energy ordering of subshells and orbitals. The periodic table acts like a coordinate system that is read from left to right and top to bottom, moving from lower energy to higher energy. The first two columns of the periodic table make up the S block. You can imagine helium as existing right here next to hydrogen. The last 6 columns, excluding helium, make up the P block. The transition metals form the D block. In the bottom 2 rows, the inner transition metals form the F block. For the S and P blocks, the period number corresponds to the shell number. However, the first D subshell is n is equal to 3 shell, but shows up in the 4th period of the periodic table. Similarly, the first F subshell belongs to the n is equal to 4 shell, but occurs much later in the periodic table. It is important to remember that after 6s comes 4f, and after 7s comes 5f. Using the periodic table, we can now determine the energy order of the subshells. The energy order is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p.